A parabola, you could have a parabola that opens up or down. And all the ones we're going to be looking at today, they're actually the center of them, the vertex is going to be at the origin. So if you have a parabola that's opening upward, like this, or it's going to look like this. Parabolas that look like this, they have the standard form, x squared equals 4 times p times y. Notice only one of them is squared, not both. Only x is squared, but not y. It's going to be this when p is greater than 0. It's going to be this when p is less than 0. And if it's left and right, that's not really a function, but you still might see them here. It's going to be either this or that. You're not going to have both. It's one or the other. If it's left and right, that's y squared equals 4px. P is the distance called, right there, the focal point, P. Basically, if you have a dish at home, and you have dish instead of a cable, it's round like this, and you have a receiver there. The receiver was placed in that spot for a reason. Why? When the wave hits that dish, they're all going to bounce through that point. If you're on the roof working there and you move that receiver, now you're not getting the signal. So there's a spot you want to make sure that the reflection. You can see that even better with light. If you have like a shiny object, like you break, let's say, a Christmas ornament, and you shine a light at it, the inside of it is kind of shiny. I'll just pretend this is like a piece of that ornament that you broke there. And you shine light at it, you see the light like this. One beam will come this way and will deflect maybe in this direction. Next one comes in this way. It bounces back in that direction. Next one goes this way. Yep, it is. And it bounces back in that direction. That point where all the beams come out, that's your P, that's your focal point. So your satellite dish, if you have one of them, it is designed on that principle. And your receiver should go in that spot there. If you put it in that spot, you're getting the signal. You put it right here, you're getting a weak signal. You're getting this line, but you're not getting the other ones. So P has actually a couple of purposes there, not just one. We have a line here. I'm going to show you actually. The book does a good job graphing. They do better than me. I'll take this picture and put it there. Can you see that picture? Notice that if you have a parabola that's going this direction, the distance from here to there is called P. We have a line that's perpendicular to that in this direction. Directrix. Somebody asked me, is that where DirecTV, the name, came from? Couldn't tell you. Could be. But what this one tells you, that if you pick any point on that curve, the distance from that point to the directrix and to that point should be the same. That's how you know how tight, how flat the curve is. That's the purpose of it. So if P here is 1 unit, then P has to be 1 unit in this direction. If P is 2 units from the center, the vertex, that's called the vertex here, then directrix has to be 2 units back there. So let me take an example and see how I'm going to graph it. With an example, it'll make more sense. Let's say I want a graph x squared, well, this is y squared. Y squared equals what? 12x. Let me pull my notes. We said if you have y squared, x is not, the graph will look like this. It's either going to be this one or that one. It depends on p. So let me match it with the form. The form for this is what? Y squared equals 4p times x. So when you compare these two equations, the 12 must equal to what?
3.
Well, 12 is 4p. You're right. I know what you're thinking. P must be 3. Is p positive? Which way is it going to go? When p is positive, it's going to be to the right. When p is negative, it's going to be to the left. I forgot to write that here. So my graph is going to be to the right. And I'm going to use a pencil and an eraser in a second. So I know it's going to open to the right. P is what? 3? 1, 2, 3. That's where P is. At 3, 0. It says my graph is going to open to the right. So what does that mean? Let me get a pencil. Do I have an eraser? Good eraser. I'm going to need it. This is not bad. I'll make a light there. Well, this is one pointing to the right. Right? Can you see it? This is also one pointing to the right. This is one pointing to the right. Which one of them? How do we know how tight, how narrow, how wide the graph is? And that's where the directrix comes in. So let me erase this. I should have left it. Can you probably still see him there, right? So my directrix now is going to be the same distance from here to there. So if that's 3 units here, directrix is going to be 3 units back. 1, 2, 3. That's where it's going to go. A line going up and down, parallel to the axes. Now remember what I said. If you pick any point on the graph, the distance to the focal point to P should be the same as this. Well, if I go with the, you can still see the smudge up there, right? If I chose this graph here, the first one, and I pick this point, is that distance the same as this? Not even close. If I pick this one, the middle one, I pick a point on it, is the distance from here to P the same as that distance? Still not yet, right? What about if I pick this one? Is the distance to P here the same as that? That looks close. So out of the 3, that looks the closest one. Well, I don't want to be guessing going, oh, is it this, is it that? So I came up with the way of doing it. What is P equal to here? 3. The equation for this line is what? X equals -3. What is the distance from here to there? 6 units. So from this point, go 6 up. 1, 2, 3, 4, 5, 6. And go 6 down. 1, 2, 3, 4, 5, 6. Your graph is going to look like this. Now you say, why'd you use 6? Why double the distance? What's the distance from here to there? 6. What's the distance from here to there? Because I went straight up. What's the distance from here to there?
6.
6. That's why you want that 6. That distance is twice p. 6, so you want to go up 6, and that will tell you the graph should be that wide. This is the vertex, 0, 0. Let me try another one. Y squared equals negative 8x. Again, only y is the square, and when y is the square, that's left or right. So my graph is going to be either left or right. The form I'm trying to match with that one is what? Y squared equals 4p times x. So negative 8 equals 4p. What's p? Negative 2. My focal point is going to be a negative 2. That's where p is. So my graph is going to be to the left again. My directrix is going to be 2 units back. So if this is 2 here, let me go 2 back. It's going to be this line. And the distance from here, this is x equals 2 here. The distance from here to here is how many units? Is that a 4? Let me go 4 up. 1, 2, 3, 4. 4 down. 1, 2, 3, 4. So my graph should look like this. That's the graph of that parabola. One more example, maybe, then I'll give you a real life example. X squared equals 4py, x squared, not y here. So the graph is going to be up or down, it depends on p. Oh, I already gave you a hint. X squared equals 4y, I didn't mean to write the p there. 4y. So that's x squared equals what? 4py. 4p equals to what? 4. P equals 1. Since x is the squared, it's going to be either up or down. Since P is positive, it's going to open upward. That's the vertex. P is going to be up there. So this is what? 0, 1. 1 unit high. My directrix is going to be parallel to these axes now. This is y equals negative 1. And what's my graph looks like? Again, the distance from here to there is 2 units. Let's go 2 to the right. 1, 2. 2 to the left. 1, 2. That's what the graph looks like. The parabola. If you log into our website, the college, you will see my picture on that bridge, standing on the bridge I built with the high school kids. And what I did actually, I used this math because I wanted everything pre-cut before we build it. I sent an email out. We're going to be building a suspension bridge after we went over it. Tomorrow at 4 o'clock, we're going to build a suspension bridge. Come cheer us on. And we started building at 2 o'clock, so I had to have everything pre-cut. And what I did, I said, I'm going to build the bridge, and I had in mind what the picture is going to look like. I said, this is what the bridge is going to look like. Golden Gate Bridge. I had these, I'm just showing you one piece of it. We had these pillars actually to hold it. That's what the Golden Gate Bridge looks like. And you have the bridge like this. Symmetric. I'm a little bit off there. And you try and find what the height of each piece, that's what civil engineers, by the way, do for a living. If you decide you want to go in that direction, you probably see in some of these bridges there. The pieces come pre-cut. You know? They delivered to the site pre-cut. Somebody did the math for them, told them how tall each piece to cut it. So when they show up, you just got to connect them, ready to go. Well, how do we know, how high each piece is? How do we figure what that is? So let's make a bridge. The one we built last year was 8 feet long. We did 2 of them, so 16. So you have another piece right here, another one right here. But that's what the Golden Gate Bridge looks like.
I was there this summer.
Where?
The Golden Gate Bridge.
Were you? I was there a couple of times. Beautiful.
Yeah.
Every time I go, it's foggy.
I'm actually very.
When yeah, it is actually one of the prettiest sights to see on a nice, beautiful, sunny day. See that bridge design. That's an old bridge too. It's not a new one. But somebody sat there and figured actually what this. Let's assume we want the length from end to end of the bridge, like this piece. Let's say it's 4,200 feet. And let's assume the height of that is 300 feet or meters, whatever they're using. We'll say feet. I can tell you what each piece is. You tell me where you want to put them. If you say I want to put them every 100 feet, I can tell you how tall each piece, just with these 2 measurements. Well, so how do you do that? You come in and you set your axes right here. You go, this is my y-axis. Right? And this is my x-axis, right there at the bottom of it. Now, if this piece is not touching the ground, I know how high this is above that, and I can add that piece to it. But I'm going to assume the road goes actually all the way there. But if it's not, again, just whatever that little height there between this and that, add it to the height of each piece. But let's say this is our road. So that piece touches the ground, so it's 0 there. That makes my life easy. We know the coordinates of one point. We know what that point is now. What's the coordinates of that point? If this is the y-axis and this is the x-axis, what's the x value, what's the y value there? 2100, I'll take it, by 300. Notice that's a parabola. So it's up and down, so that means what? X squared equals what? Yep. If I know what X and Y is, I'm done. I can tell you what P is. I can tell you what the equation that described that bridge now. X in this case, what? 2100 squared equals 4p times y. What is y equal to? 300? Is that 1200p equals what? 2100 square, big number. What is p equal to? 3675. So the equation that describes now the Golden Gate Bridge, the height of any piece, 4 times P, which is 3675, times Y. The equation is what? Y, this number when you multiply it is what? 14700 equals x squared, or y equals x squared over what? 14700. Right? You said you want the first piece to be when x is what? 100 feet away? So what's the height for the first one? X equals 100. Take 100 and square it. Plug it in here and divide it by 14700. The first piece is short, 0.68 feet. You need 2 of them. One on this side, one on that side. The next piece, 200 feet, you want it? When x equals 200. What is 200 squared divided by 14700? 2.72. You need 2 of them. One on this end, one on that end. The next piece, 300 feet away. What did I do?